So we've looked at fitting a polynomial to some noisy data. So let me run this program and let's see what happens. Okay, so this program just fits polynomials of different degrees by essentially minimizing the mean squared error between the polynomial and the data. So this is a degree 1 polynomial, namely a straight line. Degree 2, 3, 4 looks the same, 5, 6, okay, degree 8 polynomial. And we notice that as we increase the degree of the polynomial, we are able to track the data better and better, right? Is that a good thing? Should we track the data better and better? And in particular, should we increase the degree of the polynomial sufficiently so that we actually pass through all the data completely, okay? So let me just complete this. And then if you actually plot the mean squared error, there's the mean squared error, namely the difference between the curve and the data itself as a function of the degree of the polynomial you fit to the data. You notice that it starts off high for some linear regression, fitting a line, and then slightly better for quadratic, cubic, so on and so forth. And it keeps going down, right? So if you look at this data set, you can look at it here. X list is 15 times 1. It's got 15 numbers, or you can go length X list or size X list, right? So it's got 15 data points. What degree polynomial do we need so as to be able to completely interpolate or pass through every single one of the data points? What polynomial degree do we need? Let you guys think about it for a second. Okay. At this point, you should pause the video and think about the answer to that question. Okay. The answer is a 14th degree polynomial, right? So if you have a 14th degree polynomial, like of the form, and I'm just going to write it here, it's not meant to be a legal MATLAB statement, but I'm just going to write it here. So b0 plus b1x plus b2x squared dot 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 until b14 times x power 14. So if you have a polynomial like this to predict y, then how many unknowns do we have? We have 15 unknowns because we have the constant term and then the 14 coefficients of x squared till x power 14. So we have 15 unknowns and we have 15 data points, which means that if we actually want to solve the system yi equals b0 plus blah, 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 xi power 14 for I equals 1 to 15, we'll have 15 equations and exactly 15 unknowns. We can typically, if we have some random data set, we should be able to solve that because it's a 15 equations and 15 unknowns problem. So the guess is that if we use a 14th degree polynomial, this mean squared error will go all the way to 0. Okay, so let's check that if that's true. So let's actually increase the polynomial order to 14, and let me run the program again. Like I said, this was just meant to be a scratch pad. Okay, so let me run this thing. And this program itself is basically the same as the one that we wrote last time. We loop through the degree of the polynomial. We construct this X matrix. I've constructed the X matrix here slightly differently from the way I constructed it in the previous program or video, because we don't have to construct the X matrix from scratch for every order polynomial. We just have to append to the previous X by a column of X power whatever, right? So that's what's being done here. And then when I'm computing the mean squared error, I'm actually, again, not looping over all data points. Rather, I'm using this formula It's as we recall, if you recall, um, the mean square error is given by y minus xb transpose times y minus xb. That's the sum square error, and then if you divide by n, that gives you the mean square error. Okay, so I'm just using this matrix formula directly, and I'm using the backslash formula for doing the regression. And I'm actually storing the regression in what's called a cell array. What it is doesn't matter. You can look it up. I might post a separate video that describes what a cell array is, but I'm just storing each thing in a separate cell array. You can just replace this, delete that, and everything should still work, right? Okay. Okay, so let me run this. Now that I've increased it to polynomial order 14, let's see if the mean square error goes all the way to 0. Okay, let's run it. Okay, so that's linear. I'm just pressing enter here. Okay, so notice that things are starting to become weird, but you will notice that things are also starting to, well, go pretty close to the data points. So if you actually zoom in, of course, the y-axis has increased dramatically because the actual curve doesn't actually stick close to the data points. It passes pretty close to the data points. Let me just zoom in here. It passes pretty close to the data points, but far away from the data points, between two data points, the curve does some of these weird excursions, which is actually a property of polynomials, these kinds of polynomials. It's actually a bad property of polynomial approximations. In any case, we've just gone up to polynomial degree number 12. Let me press enter a couple of more times and we'll see 13 and 14. Now, if we zoom in to here, you should see, well, it seems a little bit off, and that's only because the discretization to which this curve has been plotted. So let me actually change that. Let me change that to xlist fit. Xlist fit is instead of 600, let me make that 6,000 or 60,000, doesn't matter. And then let's run the whole thing again. Okay, so if I zoom in, hopefully things will be such that things are very passing right through the points. It looks like now the y-axis is still 2000, so maybe it's not practical to zoom in all the way. But it looks like it's passing right through. I guess now it's starting to not pass through, but again, that might just be the fact that I'm not necessarily having enough points on that approximation. Okay. In any case, if you actually see what the mean square error is, notice that it starts out high for a linear polynomial and then goes down, and then at polynomial degree 14, it's actually gone all the way to 0. Well, has it gone to 0? So you can zoom in right here. Notice that the y-axis is changing. So it looks like it's really close to 0. If I look at MSE list, it says this is 0, but of course it's not exactly 0. If I go 14, 10 to the minus 16, okay? It's incredibly close to 0. So it's true. So if you have 15 data points, a 14th degree polynomial properly constructed will pass essentially through all the data points, or at least can be made to pass through all the data points to essentially very good precision. Right? Is that a good thing? Well, clearly, this function is bad, right? This function, if you recall what the data looks like, let me plot the data separately in figure 3 or something. This is what the data looks like, right? This is what the data looks like. This function that happens to pass through every single one of the data points has these huge fluctuations. Okay, so that's clearly bad. It turns out that that's actually an artifact of using polynomials. Not all things that pass through all points will have these huge excursions, to be fair. You can, for instance, use what's called a piecewise linear approximation of the data. And that will actually not have these huge fluctuations. It might, well, it will go through all the data points, but it won't necessarily have these huge fluctuations. What I mean by piecewise linear is you connect this point to this point, this point to this point, and so on by straight lines. And that would be some kind of a model as well. And that model will not have these huge 10 power 6 excursions. It will stay within the data range. Okay. In any case, this weirdness is mainly due to the fact that we're using polynomials. So don't use higher order polynomials. That's moral number one. Moral number two is, should we be fitting a model that goes through all the data? And you can sort of see immediately from this data that perhaps you shouldn't do that, because if you do make that kind of a fit, what you will be doing is fitting or making your curve pass through all the noise, right? So you are treating the noise in the data as truth and fitting your model through all the noise as well as the actual pattern. So ideally, you don't necessarily want to fit your model to all the data perfectly. So what should you do? What's the optimal, say, polynomial order or model complexity you should use? Okay, so that's a question that it turns out is at the center of machine learning and fitting functions to data and so on. So it's one of the most important questions in this field. How complex should your model be, and how closely should you approximate your data, right? Given that the data has noise. Okay. We will address that question in the next couple of videos.